Check it out now, y'all.
nanoHUB-U, online instruction.
Greetings everyone, welcome to lecture 4 of week 4 of Atoms to Materials. Today we're going to talk about the quantum harmonic oscillator, and we're going to do statistical mechanics of the quantum harmonic oscillator. This was motivated in the previous lecture by the fact that if we use classical mechanics to describe solids at low frequencies, the specific heat that we predict is very, very different from what we observe experimentally. Based on the equipartition of energy principle, we would predict using classical mechanics that per atom, we have 3K, a specific heat equal to 3K. And we know that that's only true experimentally at relatively high temperatures, and the specific heat goes to zero at low temperatures as temperature goes to zero. So we're going to address these issues today. So let's retake where we left off last lecture. We wrote the quantum mechanical Hamiltonian for the harmonic oscillator and solved the Schrödinger equation, and the energies, the eigenvalues, the allowed energies are this, okay? And h bar omega is the quantum of energy in a harmonic oscillator, okay? The quantum of energy is proportional to the frequency of the oscillation, and the allowed states are 1/2, then 1/2, 1.5, 2.5, 3.5. So the energy difference between allowed states is h bar omega, and the lowest possible energy of the system is 1/2 h bar omega. Okay. Now our task is to obtain the partition function from which we can do thermodynamics. So we're going to use the canonical ensemble. I have to sum over all possible microscopic states of my harmonic oscillator, and that means summing over all possible values of n, the quantum number, and I know the energy for that state of with quantum number n. It's h bar omega times 1/2 plus n. So that's the problem I need to solve, is doing a sum from n equals 0 to infinity. Those are all the possible states of the system, okay? The quantum number, the oscillator could be quantum number 0 or 1 or 2 or 3. That gives me a straightforward way of counting microstates, and I just need to add this number up. I'm going to rearrange the sum a little bit, okay? The term associated with the 0 point energy comes out of the sum, and then I have this sum where I have to do, again, the sum goes to infinity, to do a number to the power n, and I have to sum from n going to 0 all the way to infinity, okay? So that's called a power series, okay? And let's write it here in an abstract way where I have x to the power n. And I'm going to do a slightly more general case. Instead of summing to infinity, I'm going to sum up to a given number n, and then we're going to make n tend to infinity. And so that's the sum, okay? It goes 1 plus x squared all the way to x to the power n. And now what we're going to do is multiply this sum times x, okay? So I just shift all the terms by 1, right? So I start at x plus x squared and so on and so forth. And now what I'm going to do is subtract these two equations, left hand side and right hand side, okay? And with that, just after a simple algebra step, I get to this expression where I can have a closed form solution for the sum of these n terms, okay? You can see that on the right hand side. Now, in our partition function, we need to make n tend to infinity. And you can see that this term here, that's where n appears, okay? So if x is less than 1, that term for n tending to infinity goes to 0, and the sum is 1 over 1 minus x, okay? Let's check our term here. This would be x, okay? And you can see very easily that that is less than 1, okay? H bar omega and beta, they're all positive, okay? KT, temperature is always positive, of course, and the frequency has to be positive. So x is less than 1, and so this infinite sum converges, and I can write it down like that, okay? So very, very easily. Remember here I have this term that comes from the 0-point energy, okay, in the numerator. So that's great. We obtain the partition function for the quantum harmonic oscillator by summing over all possible microscopic states. And then if you remember, I can obtain the average energy taking the derivative of the log of the partition function with respect to beta, okay, 1 over kT. So I can do that very easily here, and I get this expression for the energy, okay? That's a little bit convoluted, but you can clean it up, and it cleans up very nicely, okay? And I obtain this expression here, h bar omega times 1/2 plus something. Now, remember, this is the energy, the average energy of an ensemble of harmonic oscillators at temperature T. Okay? Remember, the energy of a single harmonic oscillator, E sub n, is h bar omega 1/2 plus n. So this second term here in the parentheses is an average population, average n, okay, average occupation number. How many, what would be the average value for the quantum number n? And with that, that is going to define my average n, okay? And that is the excitation of that particular harmonic oscillator, okay? In average, at what level of energy this quantum oscillator will be for the particular energy, okay? That expression there for n is called the Bose-Einstein distribution, okay? Of course, all of you know Einstein. Bose was a physicist from Bangladesh who derived this equation initially for photons, and then Einstein generalized it for phonons, okay? All right, so we derived the Bose-Einstein distribution, and with that we can do additional calculations. So I have an energy now as a function of temperature. I can compute the specific heat, as you see there. Specific heat is the derivative of the energy with respect to temperature. I'm going to do that in 2 steps. I'm going to take derivative with respect to beta, and then derivative of beta with respect to temperature. So let's write it down. Okay, I'm going to have negative k over kt squared, and I have to take the derivative of this expression with respect to beta. So I'm going to have h bar omega coming from this prefactor, and then I have to do negative. So I'm going to change the sign. I need to take the derivative of the denominator, so I have another h bar omega that comes out. and I'm going to have e to the beta h bar omega minus 1 squared, and of course e to the beta h bar omega there, okay? That simplifies to k h bar omega over kt squared, okay? And then I have e to the beta h bar omega, e to the beta h bar omega plus 1 squared in the denominator. Okay, so you can see now that the specific heat, as temperature goes to 0, beta goes to infinity, and you can see these exponentials. The exponential in the denominator is squared, so that's going to dominate, and it's going to make the specific heat go to 0 at 0 temperature. Okay, I can also, as you know, compute the free energy directly from the partition function, and here's the expression for the free energy of a single harmonic oscillator. Okay, so let's look at these functions in a little bit of detail. What I'm showing here is the energy as a function of temperature for the harmonic oscillator, both classical, okay, in green, and quantum mechanical in red. Okay, so at relatively high temperatures, these two average energies are the same. Okay, the classical limit works, and the classical and quantum mechanics give the same answer. What happens is, as I decrease the temperature, I'm removing energy from the system, and classical mechanics allows me to remove the energy of this oscillator entirely. Okay, at 0 temperature, the oscillator is not moving, the two atoms are sitting still. However, we know that quantum mechanics doesn't let me do that. There's a 0-point energy that remains there because of Heisenberg. Heisenberg tells us you cannot stop this oscillator completely, because then you would know both the velocity and the position with infinite accuracy. So there's always a little bit of energy that remains, and that energy is 1/2 of h bar omega, and that's called 0-point energy. Okay, so that energy that remains at 0 temperature is called 0-point energy. Okay, so that's energy versus temperature. If you take the derivative of this curve, you have the specific heat, and here you see the classical specific heat for a single harmonic oscillator. Okay, in 1D. This is not for one atom, but for a 1D harmonic oscillator. Each degree of freedom carries 1/2 of kT. I have 2 degrees of freedom, so I have kT of energy. The specific heat is K, Boltzmann constant. Okay, and you see here that the classical, the quantum expression correctly goes to 0 in the shape that's very similar to what we saw in the experiments that I showed you during last lecture. Okay, so by applying quantum statistical mechanics to the problem, we get the right behavior for the temperature-dependent specific heat of a harmonic solid. Okay, and again, this shows us and allows us to understand how the classical regime is when kT, when the thermal energy is high, large, compared with the quantum of vibrational energy, that's h bar omega. So if kT is larger than h bar omega, you're in the classical regime, and classical mechanics works. That's the regime where MD, molecular dynamics, classical molecular dynamics works. If you're at a low temperature, a temperature below the characteristic vibrational frequencies, vibrational energies of your system, then you're in a quantum regime, and the classical approximation breaks down, whether you're in the harmonic approximation like what we're dealing with now, or in a general anharmonic case, like when you do molecular dynamic simulations. In both cases, if you're at very low temperatures, classical mechanics breaks down, and your predictions are going to be compromised. Not that you cannot use molecular dynamics at low temperatures, but you have to be aware of these limitations. Okay, now we've been dealing with a single harmonic oscillator living in 1D. Okay, single position, single momentum. We know that a molecule or a solid is made out of 3N independent oscillators. Okay, so when I have 3N independent harmonic oscillators, this is my Hamiltonian. Okay, I have the energy of the ground state, and then based on what we learned with quantum statistical mechanics, we can write the free energy of this set of 3N harmonic oscillators as the energy of the ground state. This is the energy that you would typically obtain in an ab initio calculations when you relax the structure. Okay, you bring everything to zero force and zero stress, you get a total energy. That's the energy, that's the ground state energy. And this term here is the 0 point energy. Okay, that's the energy, the additional energy that you have at 0 Kelvin, just because you cannot remove all the thermal energy out of the system. And the last term here is the thermal energy, that is the contribution that comes from the finite temperatures. Okay, and similarly, well, you see, I guess here the important aspect is that you have a sum over the frequencies, the characteristic frequencies, the normal mode frequencies of the system. So you have a sum over your 3N vibrational frequencies of these terms. Same thing with the specific heat. Okay, the expression that we just saw, and just add up the contributions of each of the independent harmonic oscillators. This is very important. Within the harmonic approximation, the system can be described as a set of 3N independent harmonic oscillators, and that's what allows me to add up the free energies and add up their contributions to the specific heat. This is for a molecule. If I have a crystal, a harmonic crystal, I know that I'm going to have a set of frequencies that depend on K, okay, on the wave vector in reciprocal space. And this K number lives in the first Brillouin zone, and I, the index here, is the number of atoms, actually the number of degrees of freedom inside the unit cell. So that goes from 1 to 3N, N being the number of atoms in the unit cell. If you remember, K tells me how the displacements change from one unit cell to the other, and it allows me, this continuum variable K allows me to describe an infinitely large crystal with a finite set of modes, okay, or in a way that I can count. So the same equations apply. The free energy has a ground state term, and also then a sum over all possible frequencies of the 0 point energy and the thermal energy, and the sum over all possible states is broken up here explicitly into two regions, into two sums. One is the degrees of freedom within a unit cell, and then a sum over the K vectors. Okay, that's typically done as an integral in the first Brillouin zone. Of course, when you do it numerically, it goes back into being a sum. Okay, and there's several models that have been proposed of how to compute these frequencies and how to do the sums. Einstein proposed originally to describe the 3n modes as all with the same frequency. Okay, this is imagining that each atom is attached to a fixed point in space and with a spring, and it vibrates around the fixed location with the spring. Debye created a slightly more convoluted model where the frequencies are obtained from a continuum elastic medium. And of course, what we learned in the previous, in week 3, is that from the dynamical matrix, which is this Hessian matrix with K dependence, okay, I can obtain the set of the dispersion curves, the entire set of frequencies for a system with very high accuracy. Okay, and we looked at these results for aluminum during week 3. So if I have all these curves, if I have the frequency, all the frequencies in the unit cell as a function of K, I can integrate these equations numerically and obtain an expression for the free energy. And with that, I'll finish this lecture, and we'll talk about in the next lecture, in lecture number 5, we're going to talk about how these concepts of statistical mechanics can affect the way we do molecular dynamics simulations and how we control temperature and pressure in MD simulations. Thank you very much.